Katoa. Thank you, Tavy. Good morning, good afternoon, and good evening, I guess. It's pretty amazing to be presenting here in New Zealand first thing early in the day. Nobody else is in the building yet. I'm sitting in my office and in Christchurch, New Zealand, and everyone else is all around the world at different times. So today I'm presenting some work that I've been doing at Fox Glacier, Te Moeka o Tūawe, so sort of looking at morphological evolution at Fox Glacier. This glacier's, I've been working at Fox Glacier for over about 15 years now, so it's very dear to my heart. At one stage I also worked as a glacier guide there, so I've got a long affinity and a great connection to the Fox Glacier. So we're going to look at changes at this glacier this morning. So just because we are an international audience, just where am I talking about? So I'm speaking to you from here, Christchurch, Ōtautahi, in the South Island of New Zealand, and basically Te Moeka o Tūawe or Fox Glacier is directly west of me, over the other side of the Southern Alps of New Zealand. Okay, it's we kind of go to the slightly more zoomed in version. You can see Fox Glacier, and it is it's got another sort of quite famous glacier, Franz Josef Glacier, is immediately to its north. Very high profile glaciers and very interesting sort of geometry. You'll notice that they've got really, really large accumulation areas that feed these very narrow tongues. And my talk today is basically going to be focusing on this terminus region of the glacier. So got a few kind of local terminology on this map just to help people sort of get orientated. So this is the very lower portion of the Fox Glacier tongue, and we've kind of got the terminus region that we're focusing on, but we also have this sort of region that we call Victoria Flat, which is a sort of local's name. It's quite a large flat area of the glacier near the tongue, and then we've got a sort of ice fall. So the glacier, as it's coming down this narrow tongue out of the really big accumulation area, flows through quite a steep upper ice fall. Sort of the ice comes into this area that it's much more mellow, sort of broadens out, flattens out. Then the ice travels down through another not so steep ice fall into the terminus region. So you'll sort of hear me using some of these terms as we go about the talk this morning. And also on this map, I guess you can sort of see the changes in the glacier. 2009, this was the length of the glacier down by Straight Creek, and our last survey is 2019. The glacier is much shorter and smaller. Now, people have been interacting with Fox Glacier for centuries. There's a lovely legend about Hine Hukatiri and Tūawe, which if at the end of our talk we've got a bit of time and people are interested, I can relay that story to you. Back in the late 1800s, Sir William Fox, who was New Zealand's first premier, visited the region and created this fantastic watercolour capturing the sort of size and extent of the glacier at that time. By the 1920s, late 1920s, early 1930s, glacier guiding became a really popular activity on the glacier. And the picture here, 1948, glacier guiding started off as quite a modest affair. And then today, you'll see, due to changes in the terminus region, helicopter access is the primary way that tourists access in the glacier. So Fox Glacier, not also very interesting and very from a glaciological perspective, but it is an extremely important glacier in New Zealand economically. So it's, of course, times are changing at the moment. As you know, our borders are closed, so we don't have a lot of tourists visiting the glaciers. But prior to the COVID lockdowns, these regions, got hundreds of thousands of people visiting them every year. They're real draw. These Fox and Franz Josef Glacier, real draw cards of people coming to New Zealand. So the Fox Glacier, like its neighbouring Franz Josef, highly dynamic glaciers, and that's part of perhaps the interest in them, both from a tourist perspective and from a science perspective. They, throughout the years, throughout the decades, they have had multiple advances and retreats. So even when around the world, and even indeed around New Zealand, when the majority of our glaciers have been getting smaller, receding, Fox and Franz Josef Glacier have both been going through these almost decadal oscillations of advance, retreat, advance, retreat. So you can see this on these length change graphs. Quite an extensive period of advance at both glaciers through the sort of mid-1980s to culminating in about 1988, 1999. We saw a period of retreat and then yet another advance. The most recent advance was from 2004 through to 2008. But since then, both glaciers have been retreating rapidly. Of course, the reason for those advances creates a lot of interest and some nice work by colleagues, Dr. Andrew McIntosh, Brian Anderson, and some others. They undertook an energy balance modelling study to look at the drivers of those more recent advances, and their research, so they're looking to see, is temperature or precipitation a key driver for these advanced phases? And their research showed that it was the lower temperatures that tend to be associated with anomalous southerly winds and low sea surface temperatures in the Tasman Sea, and then that was further linked to larger scale atmospheric circulation like the Pacific South American and zonal wave 3. There's also been previous research by colleagues looking at the influence of ENSO, the El Nino Southern Oscillation, on these highly reactive glaciers, finding that again periods of El Nino periods where we tend to have cooler sort of summers tend to result in advances further down the track. So highly reactive glaciers. If we just sort of focus in on the more, so the last 60 years or so, sort of the more recent decades, capturing sort of the last two main advance and retreat phases, what we can kind of see is that if we actually look at the rate of advance versus the rate of retreat, what we notice is that the rate of retreat is often more than double the rate of the advance, so that the glaciers are sort of more sensitive, I guess, to periods of climate warming temperatures or negative mass balance compared to positive mass balance. And I guess this is something that other workers around the world have also discovered. Imhoff did some work on Norwegian glaciers many years ago, and they made this observation about the glacier, the retreat rate being more prominent, and it also reflects the modelling work of likes of Kuhn and Ehrlemans that also noted the higher sensitivity to periods of warming versus cooling events. So I guess it's not surprising that at Fox Glacier and Franz Josef Glacier we see that our rate of retreat is really high. And also that what we're seeing is that our most recent rate of retreat is the most dramatic we've seen. And my colleague Brian Anderson, some of you may have seen this movie, but my colleague Brian Anderson, has a camera at Fox Glacier for many years overlooking the terminus, and he's created this fabulous time lapse, which just gives you, I guess, a bit of a feel for how fast the retreat has taken place, but also in generally how dynamic the glacier is. There's an awful lot going on in this image. I think when we all first looked at this footage here in New Zealand, I think the thing that almost frightened us the most was how dynamic the slopes were. As you could see, the slopes the sediments and the slopes sliding down into the valley floor, and there's some work underway at the moment exploring that. But also that just, highly dynamic, because I guess we've got that really large accumulation area feeding this very narrow tongue. So I got really interested in looking at the way the glacier changes, particularly in the terminus area, because I guess over the years there's a huge record of terminus of length change. People turn up to the glacier, take photos of the glacier, and we often look at the length of the glacier as an indication of what the glacier is up to. And we started to notice, when you're working around a glacier all the time, you start to notice distinct differences. And so I was just interested in exploring some of this morphology between advance and retreat phases. And what we often see at Fox Glacier is that during advance we see this glacier gets quite a sort of a convex profile. You know, it's, for want of a better word, it's nice and fat. There's lots of ice. We kind of have this very sort of convex profile on the surface. And accompanying that, we have these sort of areas between the glacier and the valley walls that we have this sort of gully or trough feature. Whereas during retreat phases, when we start looking through the historic photos and looking at what's been happening recently, what we see is this sort of surface profile inverts, if you like, and we start to see this sort of sunken profile across the surface, where the sides of our glaciers start to become higher than the central portion of the glacier, and we can see this sunken area commonly over the main drainage portal. So we kind of have this different surface morphology between advanced phases and retreat phases. And what we've found is this actually has some feedback processes associated with it. So as you can see, as the glacier continues to retreat and starts to thin, and we end up with all those sediments from the valley side, and you can see in that video how dynamic the erosion is in this environment. And so we get this increased buildup of sediments over the valley side onto the glacier, which essentially extends the slope of the valley out onto the glacier. And a few years ago, a colleague of mine, Christopher Gomez, we worked together looking at the changes in the rockfall hazard associated with this, because the guiding company were talking to us about, they were starting, so this is an area they used to walk the clients around on the glacier, and what they're finding is that as the glacier was retreating, as it was thinning, and as those slope materials were starting to encroach onto the edges of the glacier, essentially they were starting to see rockfall further and further out onto the glacier. So Christopher ran a sort of simple numerical rockfall model, and we took we went down to the glacier and we sort of created some 3D models of the actual slopes surrounding this particular area here, so that we could get a good sort of 3D model of the slopes, and then ran some rockfall simulations just to look at how the change in the glacier profile from this more convex profile to this more sort of slumped profile, what the implications of that were for rockfall run out distances. And as you can see there, as the glacier was starting to retreat and it was starting to thin, we were starting to see rocks coming further and further out onto the glacier. I think we sort of had something like about it's like 52 meters difference between the different scenarios. We ran a large number of scenarios, and that with the topography as it was becoming in a more retreat profile, the rocks were getting about 200 to 220 meters further out onto the glacier. And of course, at that time, in 2012, 2014, we still had a slight catching feature, if you like. We still had a slight trough at the edge of the glacier on some sides, but as the glacier has continued to retreat, we've lost that altogether now. So on this lower portion of the glacier, we got to the situation where the debris apron from the valley sides encroached right out onto the glacier surface. We ended up with no trough at the margin and increasing issues with rockfall coming out onto the glacier. Hence, at that time in 2014, the glacier guiding company Fox Guides abandoned guiding on the lower glacier altogether. So we used to walk, the clients used to come up here and get onto the glacier and go for a walk around. That got completely abandoned, and now the only way that the clients can experience the glacier with the guiding company is by flying that helicopter into this area that I mentioned earlier called Victoria Flat, which is this nice broader flat area, because the hazards down here as the glacier retreated just became too great. So that's a feedback, I guess, from the morphology, the way the glacier shape changes. And so it wasn't only the sort of surface profile that changes. But when we look at the glacier in plain view, we can see that during advance, we also get this, the terminus forms this almost nice straight line across the valley. And when we're in retreats, we get this, sometimes I describe it as a horseshoe shape, this kind of U shape, where what happens in retreat, we start to see yet again those slope processes having some influence, where the ice on the glacier at the margins gets left behind as the melt rates and the retreat rate through that central portion outpaces it. And again, this is to do with the slope processes, you know, and we there's, you know, lots of great work from many glaciologists in the past around the suppression of ice melt under debris. So as the glacier thins, slope debris comes down over the margins and suppresses the melt. And so what we have is the edges of the glacier sort of get trapped under the slope processes. We can see a photo here, and we end up with these sort of lateral wings, if you like, down the side of the glacier. At Fox Glacier, this is exacerbated on this northern side further due to the very narrow glacier valley, where this sort of northern side actually gets a lot of topographic shading too from the very steep valley sides. So just going to visit the glacier, when you start looking at some of these things, you wouldn't necessarily even have to know what, someone wouldn't have to tell you whether it was advancing or retreating. If you actually turn up and have a look at the terminus, some of these really characteristic features will give you a clue as to what phase, what state the glacier is in. So moving sort of more recently with our glacier, because we've been surveying, we always survey the terminus of the glacier. Back in the day, used to, was done with, you know, theodolite. Then we used to use GPS, walk around the terminus. All this increase in rockfall makes some of these field activities a bit more challenging. And of course, I'm sure like many of you, we've turned to the use of drones or UAVs to do glacier surveying. So we've started going to the terminus region, and got some great technicians here at University of Canterbury that do a lot of drone flying, and we can put the drone in the air, take a good series of photographs, and then use structure from motion software to create our 3D images. So they give us the ability to map the position of the terminus. But the other thing that's of course been a great sort of benefit of utilizing the drone is that we also get these 3D models. That means we start to see even more of the morphology. We can start looking at the surface morphology of the glacier more closely as well. So we're not just mapping where it is in the valley, but starting to spend more time looking at how it looks as well. And so this is some work we did in 2018, and we sort of, so you can sort of see some of these features that we were seeing from just the oblique aerial photographs being captured in the 3D models. So again, here's our ice being buried under our slope debris on the edges. And this collapse over the main drainage conduit really stands out in our models, where we can see that this sort of, the way as the ice is thinning, it starts to collapse into this, you get the sagging over the main drainage conduit, and then this is where the ice is starting to collapse down. And so this, what we're finding, that the collapse over the main drainage conduit is sort of setting a bit of a pace for the up glacier retreats, or the gradual collapse of the terminus up the valley is being quite driven by this by the actual position of the main drainage conduit. We start to see, you know, we get in the air and you start to have a look around, you start to see these thermokarst features like sinkholes, where you've still got your ice is starting to become even further buried with debris. We also had this really interesting, in 2018, this sort of alluvial fan is actually developing on top of terminus ice. So again, we've got our slope and we're starting to see drainage of water from the slopes onto the glacier surface, getting a sort of supraglacial stream forming that then is actually flowing over this heavily debris covered ice and creating this actual little fan. And we've actually so this fan you can see here is actually sort of perched on top of terminus ice. So some really complicated, interesting features. And so I guess all features that delaying the, when we start to get this really heavy debris cover at the surface, we're starting to see changes in the rates that the glacier can respond to climate. So leaving that, and we know, our terminus has a delayed response, and this delayed response gets even more complicated when we start having all these sort of feedback processes associated with this increasing debris cover. So when we kind of move to getting close to present day, you can see here's from our 3D model from just last year. You can see what I'm talking about here with this main drainage conduit playing quite a role in the collapse of the lower part of the terminus. Basically, by our present day now, you can see we've got this whole lower portion of the terminus starting to look really stagnant, heavily debris covered, full of sort of down-wasting thermokarst features, and this really sort of role of the drainage leading, so it's just essentially leading the retreat up the valley. The other interesting thing we can see, and you can see it, I guess this is a webcam image where here's our Victoria Flat area. This is the area up here below the waterfall where the guiding still takes place. This is now what, our lower ice fall we talked about. And we can see this whole lower portion of the terminus essentially starting to look really undernourished and in a state of sort of essentially down-wasting under debris cover. The other thing that we found when we started exploring our 3D imagery from the drone is the other interesting things you can start to see is that at the base of the lower ice fall here, when we started to actually look at the ice structures in the ice, we've got this zone of compression where the ice is coming out of the lower ice fall, and then as it's meeting, and you sort of get some compression as it's meeting the more stagnant ice in the lower valley. And so you can really start to see this transition on this lower part of the glacier from this area where we've still got quite dynamic ice. The ice is sort of flowing down the valley. We've got all these features that, like with crevassing, we've got compression, so the ice is still quite dynamic. And then we transition into the zone where the glacier, we can't see any sort of, we're not seeing any traverse crevasses anymore, and the only sort of dynamic features we're seeing is as the ice is sort of collapsing at the very terminus into the proglacial valley. So sort of showing us that this whole lower portion is very undynamic. So of course, waiting, I guess the guiding company is always saying to us, what's going to happen? What's the glacier doing? And the numerical models are really powerful, but when we start getting, the glacier guiding company doesn't want to know what the glacier is going to be doing in 50 years' time. They want to know what the glacier is going to be doing next year, 5 years, even 10 years is usually beyond a lot of companies' vision. They want to know what's happening more quickly. And of course, as we all know, waiting for things to happen at the terminus is not going to tell us very much. So in order to try and understand the behavior of this glacier, this highly dynamic glacier further, what we decided to do is we thought that we would try to get a point on the glacier that we could regularly monitor for mass flux. I guess taking an approach a bit from our colleagues that do a lot of work on the ice sheets down in Antarctica, thinking about putting in a flux gate, if you like. So a team of us went to this, but this is here's our upper icefall, Victoria Flat region. Oliver Marsh, who's now returned back to the UK, working at British Antarctic Survey. Brian Anderson, who's works a colleague here from Victoria University, who you've seen some of his work already today, and some postgraduate student. We took a thought we'd need to get ice thickness. In New Zealand, we actually have very poor knowledge of ice thickness on many of our glaciers. Back many years ago, I took a ground penetrating radar to Fox Glacier with a bunch of keen postgraduate students, and we did manage to get a good survey of the bed on the very lower portion of the glacier using a 25 megahertz ground penetrating radar. Great information at the time, but of course that part of the glacier no longer exists. So although I got a nice ice thickness, it is a moot point because there is no ice there anymore. And we tried the ground penetrating radar further up the glacier here in this Victoria Flat region, but could never get a good return off the bed. And we always did suspect, so down on the lower glacier, I got an ice thickness of 120 meters. And we always expected this Victoria Flat region to be thicker. You know, it's a big, broad, flat area. You know, if you think of it a bit like a pond. And so we always expected the ice to be quite thick there, and we could not get the ground penetrating radar through the very warm ice. So remember, we're very temperate here. This ice is very wet year round, really. So what we thought we'd do, we thought we'd try one of these phase sensitive radars. This is a radar that was designed by British Antarctic Survey, especially for work in Antarctica, and Oliver Marsh has used it extensively down in Antarctica, and so we thought we were really keen to give it a try on a New Zealand glacier, a trial. And so we took it out there and did we took some profiles across the glacier at the base of the upper ice fall, and then we did a profile down the central part of this area called Victoria Flat. And we got really nice speed returns with the phase sensitive radar. The signal got a little bit, it was less clear near the edges, as you'd expect with any sort of geophysical technique, because we get a lot of resonance from the very narrow valley wall, but we got a really nice speed return. This had to be, this is as a very controlled trial, because at this stage we still can't freely use these units in New Zealand on our glaciers because they're not shielded. This radar, you know, it sends a ramped sort of signal, a chirp that crosses quite a number of frequencies very quickly, but those frequencies also include frequencies that are used for locator beacons and things like that in New Zealand. So it's not something, so we did this as a controlled trial with the guiding company and with the helicopters that were working in the valley at the time, just to see if the unit would even work in New Zealand. But until, here's a plea to anyone listening who works with these things, if anyone wants to go ahead and get these shielded so that the signal's only going down, then I think we'd use them an awful lot on New Zealand glaciers. So anyway, I'm digressing a bit. So we got a good bed profile from the glacier. I installed a GPS onto the surface of the glacier, continuously logging GNSS. And then from there on, keep walking the surface elevation. So we've got a bed, we've got our surface velocity. And so then I thought, well, okay, we can keep monitoring our surface elevation with GNSS survey, which we correct back to a survey point in the valley. So this is going to give us a good idea about how the glacier is changing, much sort of earlier notification, earlier warning of the changes compared to waiting to see what happens at the terminus. So we'd set all this up back in 2015 and then regularly surveyed the surface elevation, and that's something that's sort of ongoing work. Now, of course, as you can see by the picture here on the right-hand side on B, this is the reality of walking around on a glacier, as most of you will be very familiar with. It is not smooth and flat, so naturally any of your surface elevation profiles are going to have a reasonable sort of variability with them. And so for the first 5 years, you know, the profiles that we were walking, when we started to look, you know, sometimes it looked slightly thicker, slightly thinner. None of these were above and beyond the normal variability that you could expect with the method being used with the topography that we were surveying. But by November last year, what we could see is the surface elevation was really, the glacier was starting to thin more significantly. And of course, this sort of thing sometimes makes me laugh a bit. So, we're running around out on the glacier with, GNSS, good expensive equipment, drones, all these things to determine ice, is the surface elevation of the glacier changing? And of course, the local guides are all like, of course it's thinned, because, they're sitting in their office and walking around on it. And you can look at the webcam and you can actually pick out rocks on the valley wall, and you can see in 2016, these parts of the bedrock only just sticking out of the ice, and by 2019 they're high and dry. So yeah, sometimes I find I think it helps keep us scientists real. We run around with all this equipment and we do all this number crunching and come up with these numbers about how these glaciers are changing, and the people that are living and working there every day are like, of course it's changing. So they help keep us grounded. Anyway, so we've got our surface elevation, we've got our bed, we can estimate and we've got our GPS on the surface, so we can estimate our mass flux of ice, how much ice is flowing through this point on the glacier. How much ice have we got coming down to potentially nourish that terminus region that we're interested in? And so we've got our mass flux. I calculated an average. So I sort of did two sort of scenarios really. So we looked at just using the average surface elevation that we'd captured from 2015 today, with this natural variability of the glacier, sometimes, elevation sometimes a wee bit higher, a wee bit lower, taking into account all this topography. And then I ran another one utilizing this most recent surface elevation, and so came up with two mass fluxes at this point, two sort of ice mass volumes coming into the glacier at the base of the ice fall. And then to just get, I guess, an approximation now, just to get an estimate of how that's ice, well, what are the losses below that point, we used some previously measured surface ablation. So I divided this lower part of the glacier into three portions based on characteristic surface features. So we've got our large Victoria Flat area where we've got predominantly white ice, glaciers quite mellow. We have our lower sort of icefall zone where the glacier is extremely broken, but still, relative kind of dirty ice, I guess. We've got a lot of crevasse traces and stuff in there. And then we've got this really heavy debris covered down-wasting tongue. And so utilizing sort of previously measured ablation rates, we can just do a estimate, looking at our surface area of each of those segments, what the annual ablation rate is, and then just do some simple kind of back of the envelope calculations to see how much ice mass we've got. And what we found is that if we actually use the average ice flux that we've been getting through the lower tongue over the last sort of 5 years, then that's more than enough ice to sustain this lower portion. But if we actually use the most recent surface elevation and recent mass flux, we don't have enough ice, slightly not enough ice to fill this lower tongue. So I guess that kind of reinforces what we're seeing, what we're observing, that we've got this lower portion of the glacier that is not being nourished with the current ice flux through that's coming down from the accumulation area into this lower portion of the tongue. So basically the glacier went like, it's the shortest it's ever been in recorded history. We've got a number of really interesting feedbacks that are related to the changes, particularly in surface debris cover from slope processes, the ablation processes that are make our terminus, when it's retreating, become very complex. Our current ice isn't sufficient to sustain the length, and so I guess from our measurements, we would sort of predict that this very lower 300 meters of the glacier is likely to collapse, and as it's not being sustained. However, because we're dealing with Fox Glacier and not some other glaciers, we can it's always a risky thing to suggest that the Fox Glacier is going to continue retreating or bits of it are going to collapse, because you always have to just look back in history and you always have to reflect back on the geometry of the glacier. Again, this massive accumulation area feeding this very narrow tongue. So very small volume of ice tied up in this entire tongue compared to the volume of ice we have at high elevation. The equilibrium line of this glacier sits somewhere around the base of the accumulation area in this upper ice fall. So you'd never say never. And so although our current measurements and the current ice flux coming through this part of the glacier appear not to be sufficient to sustain the very lower portion of the tongue, depending on the seasons, depending on our atmospheric circulation patterns, it doesn't take much to turn these glaciers around. We have, reaction times of only 5 to 6 years. Response times have been calculated at only 15 to 20 years. Of course, this year, New Zealand is heading for possibly the 3rd warmest winter on record. And although, yes, we definitely feel very privileged that we are able to be out skiing and that, and although many of us did buy ski passes, some of those ski fields that people bought ski passes for have not even opened this year. So our winter snow is very low. I think along the main divide of the Southern Alps, we're looking at only 45% of the normal snow depth that we would have at this time of year. So short of a big turnaround in spring, which if any of you have been to New Zealand, it's completely possible. We do get quite a bit of snow in spring. Often if you try to plan a holiday, you can guarantee it's going to snow. But short of having a decent spring snowfall, this year is definitely looking for being a very bad year for snow inputs into the top of our glaciers. So the situation at Fox and Friends is probably going to be, we're going to probably see that being maintained for a few years yet. So definitely picking this lower part of the glacier to disappear, and we'll end up with an even shorter glacier. This portion of the glacier, this lower ice tongue, this lower ice fall is the thing that is still dynamic. So yes, so Fox Glacier, highly dynamic, and some really interesting things going on here. And that's all I have for you today. Thank you.
Thank you very much indeed, Heather. So are there any questions for Heather? And whilst people are thinking about that and putting on the chat, just mention next week's seminar, Frank Patton is going to talk to us about the uncertain future of the Antarctic ice sheet, sound and harmony of the marine ice sheet instability. He promises this will include a piano. He also promises me this will be technically feasible, but we shall see next week. So questions for Heather on this week's seminar. Kate Winter, you can unmute yourself, or I can find you and you can,
I've unmuted myself. That was a really interesting talk. Thank you very much. I'm quite interested in the link with the guides on the ice, as well as the science and how that interplays together. And I know that a lot of kind of guides up in kind of like the European Alps, so the Rhone Glacier, have tried to kind of cover the ice in order to protect their glacier, to get people in to ice caves and up on the surface. Are the guides keen on doing something like that to Fox Glacier?
That's a great question, Kate. Thanks. And it's another area of research that I'm very passionate about is glacier tourism. And I think it stems a little bit from having worked as a glacier guide myself as well. I'm really interested in this intersection between what the glacier is doing, how the guides are interacting, and the tourists are interacting with it. And yeah, it is quite incredible what is going on in Europe with the coverings. I got sent some photos, I think, from one of the glaciers in France, that, yeah, these big white blankets over the glacier and a lot of infrastructure being built to access the glacier. Now, and New Zealand operates quite differently to that. all our glaciers on public conservation land, and so to operate glacier guiding in New Zealand, you have a concession from the Department of Conservation, and those concessions have quite a lot of conditions around, and so we have quite strict conditions on infrastructure, I guess, in the mountains. And so what we've been seeing here, so I'd be very surprised if a company was ever able to do anything like put blankets on the glacier. I mean, even building structures to get closer to the glacier is not something that's encouraged here. But what, of course, is happening and has been happening is we've been seeing a really huge increase in the use of helicopter access. And so that's been really interesting. Some of the research I've been doing at Fox and Franz and Aoraki Mount Cook, looking at this adaptation to climate change around getting people getting into the mountains, whether it be for recreation or tourism. We're seeing this huge increase in the use of helicopters, which is it's a whole interesting thing in itself, isn't it, with climate change and fossil fuels and then increase in aircraft activity. But yeah, as of yet, and the guides, I think the guides, they want to use the helicopters, they want to get the clients in that way, but there's been no talk at this stage of wanting to have any, I think most people look at what's happening in Europe and find it quite hard to believe that that is something that is able to be done, because certainly with the way our Department of Conservation concessions work, that's sort of, I want to pick my words carefully here, isn't it? Want of a better word, like interference or something with the natural processes wouldn't really be encouraged. But yeah, I do watch what goes on in the Northern Hemisphere with quite a lot of interest. Thank you.
Thank you very much. Yeah, that's really interesting. Yeah, I'm quite pleased with the approach that you've taken down New Zealand.
Any further questions for Heather? I had a lot of sympathy for your statements about unshielded antennas. We had our own experiences with interference on the same frequencies as emergency beacons we're working on from unshielded antennas. Roland, would you like to unmute yourself, or I can find you and unmute you, whichever's easier. Go for it, Roland. Roland Warner, did you have a question? You are unmuted. Okay, maybe we'll move to Ian Evans while we find out. I'm not sure what's happened to Roland there. Ian, do you want to go ahead with the question? For some reason, I can't unmute you, Ian. You might have to unmute yourself.
Oh, okay, okay.
There you go.
Thank you very much for an excellent talk. Very interesting. Brings back my memories from January 2013. But my guide was male. I don't think I had you as the guide on Fox Glacier, but at least I didn't have to use a helicopter. So my question is, what can you say anything about change in the accumulation area? The accumulation area ratio looked rather high, like sort of 90% in your image. Yes,
Ian, that's a really good question, and I wish I could say something more about the accumulation area. And maybe we don't have good surface elevation data from that accumulation area. We have very little previous topographic maps that were done with aerial surveys back in the 80s, and there hasn't been. We seem to, for the people that work with the satellite imagery too, we have a lot of issue with the cloud cover, so we don't. And it's a really important thing really, because you're quite right, a huge volume of those glaciers is all tied up in these accumulation areas, and yet we have very little information about how the upper part of the glacier is changing. So work myself and a colleague, Tim Kerr, did a few years back looking at changes on the Linda Glacier, which drains off Araki Mount Cook, and looking at the upper parts of that. Again, we had the same issue with, we're trying to get surface elevation data, and with the steep topography, the errors on it was sort of almost beyond the change we were looking at. And we were talking a lot to the guiding company, and it was really interesting because a lot of them were saying that up high, they don't, some of the changes are hard to detect because we have really year-to-year variability in snow accumulation is actually really high. So it tends to, what we seem to be feeling is that it's often this interannual variability in snow accumulation sort of masking some of the changes, the longer term trend at high elevation. But we are starting to hear reports from some of the guides about seeing increased rock exposures. So little clues like that lead us, like, it sounds like they're thinning, but we don't have very good data. Now, I know Pascal Sergey from Otago University has been doing a lot of good work lately, trying to get some volume estimates of the Southern Alps region. And so hopefully when that research comes out, we might have a better idea about what's changing up high, because that is definitely a great big hole in our knowledge at the moment, is being able to quantify the change at high elevation. Because if it's thinning up there, then that's a really, it's a whole different kettle of fish really, because most of the volume is up there, which I guess is why these glaciers are doing all right so far, because even a small, even subtle increases in the snow rain temperature threshold, most of that glacier is still going to get a lot of snow. So yeah, really good question, and we're really something we need some data for. Yeah.
Thank you very much. I was also interested in the interpretation that the advances were not due to increased snowfall, which I think we talked about in the 1990s, that Norway and New Zealand were going to be the great exceptions to the loss of ice globally with heating. But you're saying that it's not snowfall, it is periods of lower temperature that gave you the advances there.
Yeah, that's certainly the results that the numerical modelers are finding, when they actually, in the work that Brian Anderson's been doing, and he's run his model on a number of glaciers throughout the Southern Alps, and this seems to be a common thread, that they're more sensitive to the temperature changes than the precipitation changes. Of course, they do go hand in hand to a certain degree. You never can fully separate them, but that it is these cooler temperatures that are exerting more influence. So yeah, it's really interesting, and it'll be interesting to see, as if they continue, as climate continues to warm, how these relationships hold in future.
Thank you very much, Heather.
Thank you.
Hi, I've got a question from Roland Warner. Unmute seems to be not working for some reason for him. And he's asking whether you could say a bit more about the bed topography from Victoria Flat to the lower icefall. Is there a basin under that thicker ice and a sill at the top of the lower icefall? He's just curious about the future of the icefall.
Yeah, that's thanks, Roland. That is a good question. And so if I even go back to when we took the survey here, and we took points with the P-res, and of course the P-res was just individual points, not as many as this. This is the surface elevation. So our primary objective that day was getting this cross profile in to get the mass flux, and then with the time we had left, we started working our way down glacier. Now it was getting thicker and thicker as we went down. I just off the top of my head, I think the maximum thickness we got to was about, so I don't know, there's about 200 meters ice thickness, 230 ice thickness across the central portion. We were down to over 300 meters ice thickness as we were starting to head towards that sill. And So, and and one intuitively suspects that there is a bit of a basin there. It was definitely still getting thicker and thicker as I was going down. Unfortunately, we then ran out of time and had to fly back out. And so I didn't quite get as many points in this region as I would have liked. So it would be nice to get back with that equipment just to get a little bit more information. So I think that the data we got indicates that there is a bit of a depression there, but just how extensive it is, I wouldn't be able to say yet. But yeah, there's quite a volume of ice sort of sitting in that region. But yeah, it is interesting to think about that lower ice fall, and particularly if we lose that lower portion of the tongue, we will sort of have some steepening there. So would be interesting to see if that's going to have a feedback on the ice velocity and with the steepening of that lower portion of the glacier. Yeah, as you probably start to get a theme here in New Zealand is lack of data, but I'm sure I'm not the only one that has that problem. Thanks, Roland.
We have a question from Live Unlock. Again, we seem to be having some difficulty unmuting. Can you unmute yourself? Otherwise, I will read out his question. Okay, so I'll read out Live Unlock's question. Asks whether your PRES bed return strengths differ for the across flow and long flow radar profiles.
Yes, they did. So through that central portion, we got really nice returns, like the example we've sort of given here. Through the sort of very central portion, also really good returns. So in general, they were really nice and strong. But yes, certainly as we got out onto these outer edges, the bed return was definitely not as strong. So I think we're starting to get that sort of feedback interference from the valley walls, and so really nice. The signal was really clear all the way down through the central portion and through this central area, the central flow line area up higher, but the edges were definitely not as clear for sure.
Okay, are there any final questions for Heather, or have we run out of discussion there? I think we're getting to the end there, so thank you very much indeed to Heather, and thank you to everyone for attending. I have a new version of Zoom installed tonight, so I'm wondering whether this is the reason that we're having problems unmuting. So I'm going to ask if everyone would try and unmute themselves, and we can say goodbye to Heather orally. And if we can't, then obviously there's this new version of Zoom, and I'll have to try and sort that out better for next week. So if everyone would like to try unmuting themselves and see if they can, but otherwise we'll say thank you very much to Heather.
Thanks, Heather, from Hester.
Thanks, Heather.
Hey, right, okay.
Thank you, Heather.
Thanks, Heather.
Great talk.
Thank you.
Thank you.
Okay, well, thank you very much to everyone.
Thank you.
And
Thank you, thank you all for coming. Yep. And thanks, Tavy, for organising it. It's great.
thank you very much, and thank you. And we'll see how the piano goes next week. So see you all next week. Thank you very much indeed. Bye.